Before we start exploring the idea of circuits with multiple resistors in it, let's talk about the different components of Ohm's law, some key details, and let's start with current. So what current is the flow of electrons. In other words, it is the number of electrons passing by over time. And to be clear, this is not the same thing as speed. In other words, it is not a distance traveled by our electrons over time. And to explain this idea, let's go ahead and use an analogy I like of a bunch of people trying to get into a pool. And we can even label this big blue blob pool and have some people hanging out in the pool. So we'll just draw some heads sticking out of the water here to keep it simple. And maybe even draw somebody jumping in the pool, so we can even draw him in a way that it looks like he's doing a cannonball. Yay! Everybody's having fun. And the idea here is there's really no limit keeping these people from getting in or out of the pool. They can go in as fast as they want or get out as fast as they want. But what happens if we add a limit to this analogy? So what if we draw some gate here? And just so there's no confusion on what this random shape is, let's go ahead and label it gate. And let's draw some people waiting in line behind the gate. So we'll draw like 3 or 4 people maybe. And let's say only one can pass this gate every 2 minutes. But if you think about it, once they've passed the gate, they can get in as fast as they want. They can go as fast as they want. But before the gate, they're going at this sort of snail's pace. They're just sort of waiting. So effectively, since only one person can cross the gate every 2 minutes, one person enters the pool every 2 minutes. And what I mean when I say that flow is not a speed, or current is not a speed, is it doesn't matter how fast they're going. On the right, they're going super fast. I'm sorry, on the right, they're staying still. On the left, they're jumping in the pool super fast. So even though their speed is clearly changing, the flow of people entering the water is constant on both ends of the gate. And this concept is just as true in a circuit. So let's look at that. Let's draw ourselves a quick little circuit here. And let's keep it super simple. Let's go ahead and just say it's a 2-volt battery. And let's say that it has a resistance of just 8 ohms, just to keep it nice and simple. And then we can even take the time to figure out current if we wanted to. We know current is just voltage divided by resistance. And we already know what the voltage is. We just said it was 2 volts, and we just said the resistance is 8 ohms. And you can pull out your calculator if you want to figure this out, but it's pretty obvious. 2 is a quarter of 8, so that means this is a quarter, or 0.25 amps, or another way to look at it is 250 milliamps, or 1/4 of 1,000. See what I did there with 1,000 and the milli? It should be pretty obvious. But before we were interrupted by that math, we were talking about a concept that the flow of electrons is not really a speed, but an amount of electrons over time. And what I mean is, if we have electrons leave this battery along our circuit, they hit the resistor and they have to wait in line, kind of like at this gate. But once they pass the resistor, they can go as fast as they want. So even though the speed might change along the circuit of the electrons, the flow is constant, and that's the idea. And so let's go ahead and write that out. Let's write out current is constant in a circuit, or at least in a circuit like this, and that's because in this circuit, there's only one path to take. Only one path for the electrons to take. And later on, we will discuss the idea of having multiple avenues and that improving the flow, changing the current. But right now, let's just stick to the idea of only one path to take and current being constant. And while current is constant, voltage is not. In fact, electrons are flowing due to the difference in pressure. That is the voltage. And that's what voltage is a difference in pressure along the circuit or in the power source. So let's go ahead and finish writing this out. So voltage, pressure, difference. And let's explain exactly what we mean. So on one end of the circuit, we have a certain pressure pushing, and on the other end, we have a different pressure pushing. That difference of pressure allows electrons to go one way versus the other. And what we actually find is there's not much change in the voltage on each side of or each side of the resistor, I should say. There's a slight drop in pressure along the circuit before any resistor or within a circuit at all, but it's so small we really don't need to concern ourselves with it at this point. So what we find is the resistor is actually the main dividing line of the two competing voltage pressures. So is dividing line between voltage pressures. So another way to look at it is that the resistor is actually causing the change in voltage. And this is because resistors cause resistance. Who knew? And that resistance actually slows down the voltage. So in other words, it is dropping the voltage or causes voltage drops from one side of the circuit to the other. And in fact, the voltage is actually dropping, like we said a second ago, a little bit down the circuit all the way, because there is some resistance within a circuit. Any kind of wire will always have some resistance. But it's so small we don't need to concern ourselves with it. But that's the key takeaways I want you to take, or the key details I want you to take away from this video, is that current is constant when you only have one path, that electrons flow because of an inherent voltage pressure difference, and that the resistors, one way of looking at them is they are actually dropping the voltage. And if that makes sense to you, then you're ready to move on.